In this video, we're going to introduce an application of integrals that's both more theoretical and also more commonly applied in physics and a lot of the biological sciences. And that's the study of improper integrals. The word improper doesn't mean there's something actually wrong with it. It just captures a certain subtlety in the integral that involves an infinite limit. And it just means that we have to be careful in how we handle it. Let's start off with an example. A chemical reaction produces a desired chemical at a rate of e to the negative t grams per second. Here's a very traditional integration question. What amount of the chemical is produced between t equals 0 and some unspecified later time, capital T? Well, as soon as we see the word amount here, we're talking about grams, and the information we've been provided is about the rate. So what we would expect is we're going to see an integral here, and the total amount of chemical produced would be made up of the rate, which would be in grams per second. But because that rate is changing, we would have to multiply that by little units of delta t and add that up. That would give us the right units, and because these time intervals are short, we would be able to use this calculation even though the rate is changing. This is what we would have called earlier, and should still call, a Riemann sum value times little units of time to get a total amount. We also know now that we can convert this Riemann sum into an exact value, integrating instead of the delta t with a dt, but still having our rate there, and including explicitly when we want to start and stop our accumulation. If we do that one more time with the actual formula for the rate, e to the negative t, we can proceed. We look at this, we ask ourselves, can we find an antiderivative of e to the negative t? We absolutely can. It's e to the negative t again with a negative sign out front, and we evaluate that between capital T and time 0. That gives us e to the negative capital T minus, I have to be careful with parentheses here, e to the minus 0. This turns out to be just 1. And if we look carefully, it's got a double negative, so it's actually plus 1. And this term is negative. And so we end up with 1 gram minus something to do with how long we run the reaction for. When we're working on conceptual problems, one of the questions that comes up is, what would happen if we just ran this forever? What's the long-term behavior of this reaction? Well, the nice thing about that is we have another mathematical tool, which is a limit. If we're talking about running forever, what we're asking for is that final time point. Originally, our t-scale went from 0 to big capital T, and we talked about the area under the curve there. That's how we could imagine visualizing the value from our integral. But now we're saying, well, what if we take this capital T value and just push it out further and further and further? Well, that's exactly what we want to do to capture that idea of running forever. And in fact, what we do here then is take what we computed on the last page, which was 1 minus e to the minus capital T, and we would say as the large T, which is up here, heads towards infinity, this whole expression here heads towards 0, and we'd end up with 1 gram of total product. So we can conceptually break down this process into how much would we make of this chemical product between time 0 and some unspecified time, capital T. That gives us a nice antiderivative, no funny business, nothing strange going on there. And then afterwards you say, well, what if we took that upper limit and pushed it larger and larger and larger, in fact, let it go towards infinity, and then we can get a total value for the final expression. How much would be produced if we ran the reaction forever? So this is conceptually what we're going to be doing throughout this part of the unit. We're going to have a new notation for that, though, which captures the ideas that we mean here. We're going to evaluate an integral of our rate. It's going to start at 0, but instead of putting this machinery in to start with, we're going to write this as a shorthand, explicitly putting an infinity symbol where usually we put numbers, and this is what indicates we have an improper integral. It's improper because there is an infinite quantity in here. And as soon as we have something infinitely large in our calculations, we know we have to be pretty careful. Looking at the class of improper integrals more generally, what we're going to be doing is looking at this kind of formulation, an integral from some value up to infinity. This is going to be our first step every time. No negotiation, no options, no nothing. If you see an infinite quantity in your integral, it must be replaced by what it actually represents, which is the integral to a finite value. So this part here is always going to be finite as well. And then only once we've calculated that integral, then we say, oh, what happens as we push that upper limit towards infinity? What this allows us to do is separate it out, the nice clean integral stuff that we've done before, from the new infinite quantity problem, and make that an afterthought or a second phase of the analysis. We're also going to see some other integrals that look on the face of them fairly innocent, an integral between two finite quantities, but where one of the function values is not defined. And that could be an example where we have an asymptote. And if we ask for the area under the graph up to the asymptote, there's also an infinite quantity involved there because the graph goes infinitely high as we approach that value. We'll deal with these a little bit later on. The technology will be the same though. We'll imagine sneaking up on the problem point using a limit process. So we end up with something finite, and then we explore what that finite value approaches when we push closer and closer to some problem point. An important piece of terminology that goes with this, as when we've done any other limits, is we might have limits that result in a number that converge or that diverge, and we're going to say the same thing for the integrals. If we evaluate the integral and then take the limit and we get a finite number back, we'll say that the integral converges. However, if we find a limit that does not exist when we do that final step, we'll say the limit diverges. Let's apply this through a series of examples to make this a little more concrete.